Still just reviewing for the final.
Okay, what do you got?
So the first problem is, sorry, okay. Find all the zeros of the function.
Okay,
Okay, so it is x to the third plus 2x squared plus 5x plus 10
thank goodness that was no 10.
equals 0.
You'd have given me any number other than 10, it's a 20-minute problem.
Oh, really?
Uh-huh.
Uh,
The fact that you gave me 10 means that we can solve this by grouping, which is the very first thing you should try. It's kind of like when you're factoring, the very first thing you should try is greatest common factor.
okay.
When you're trying to find the zeros of a cubic, what you're looking for initially is that the ratio of these coefficients is the
Okay.
same as the ratio of these coefficients.
Okay.
If that is true, then you can solve it by grouping. And it is true in this case. Okay. Now, obviously, most cubics are not going to be able to be solved by grouping. It's
Mm-hmm.
very, very unique that you have a cubic function that can actually be solved by grouping. But that's the first method they teach you. They may or may not teach you the hard method next. They probably will. It's called the rational factor theorem. And trust me, it's complicated. But grouping is not. And basically what I'm going to do with grouping is I'm going to group those two and those two.
Okay.
Now take the greatest common factor out of the first set of parentheses,
That would be x squared.
leaving
X squared leaving x plus 2.
take the greatest common factor out of the second grouping,
Um, that would be 5,
leaving.
and that would leave x plus 2.
Now in all grouping problems, these two things are the same. If they're not, then you've either made a mistake or it does not lend itself to grouping. In other words, those ratios were not the same. Okay?
Okay.
Now, we're going to do something that you're not used to doing, but it is factoring out a binomial. In other words, if I look at this expression, there is a greatest common factor there. It's x plus 2.
Mm-hmm.
What's left over?
X plus 2 and x squared plus 5.
Yeah. And now we have factored it. Now, the exact instructions for this problem were what? Find the zeros?
Find all the real zeros or find all the zeros of the function.
Well, they're different questions, incidentally, um,
Mm-hmm.
because this only has one real zero, and it's minus 2.
Okay.
This is an irreducible quadratic, meaning it's going to produce imaginary solutions only.
Okay.
Tell that because there's nothing that can make this be 0. X squared is always a positive number, and if you add 5 to it, it's always a positive number. So it's impossible to make that 0, and the solutions are going to be imaginary. So what do we have? We have x, if we list all of the solutions,
Mm-hmm.
we've got x equal minus 2 for this one over here. And in this one, x squared equals minus 5, which means x equals plus or minus square root of 5I.
Okay.
So there's your three solutions. Now, in point of fact, if I were to graph this, it's only going to cross the x-axis in one place. So there's only one real zero, and that's -2. Imaginary zeros do not cross the x-axis. In other words, this thing might look something like this, okay, where it crosses at -2, but nowhere else. There are three zeros. Just remember that imaginary solutions do not cross the x-axis. They are solutions, but they don't cross the x-axis. Now, the net result of all of that is that usually when you're doing these problems, it kind of depends on the textbook or the teacher or whoever is working with you. But you take your polynomial and you reduce it to linear factors or irreducible quadratics, but you don't generally take the irreducible quadratic all the way down to the imaginary number. In other words, in a lot of cases, this would be your answer.
And you just leave it like that?
Yeah, because this is an irreducible quadratic, so they don't bother to take it down.
Okay.
But like I said, that depends on your teacher, and the instructions on this problem were to solve for all zeros.
Yeah, just all zeros.
Yeah, I'm not even sure you can call that a zero. I don't see how you can actually call that a zero because it isn't. But it is, I suppose, a solution. So if you want three solutions, basically you solve this even if you have to use the quadratic formula. This we didn't use the quadratic formula because it's easy enough to solve that for its imaginary solutions.
Okay.
Now, if they want you to give all factors, well, here's what they are. X plus 2 times, let's see, that was plus root 5I and minus root 5I.
I think that would be the final answer.
Yeah, well, certainly this is never going to cost you, taking it all the way down.
Yeah.
It may or may not, unless the instructions say reduce it to its linear factors and irreducible quadratics. I have a textbook, and that's what it says to do. It doesn't take it all the way down to its imaginaries.
Just reduce it to its linear factors?
Its linear factors and its irreducible quadratic. In other words, if I make that a -5, let's say that's the problem, well, now that's a real number there. In other words, x would be equal to plus or minus square root of 5, and I would have two more linear real zeros. And it would cross the x-axis in 3 spots.
Okay.
Okay? But it didn't come out to be a -5. But as long as I remembered that, I want to make sure that you can handle a tougher situation.
Okay.
It's not that hard to handle, but you got to avoid making a very common error.
Okay.
Make that minus. And this minus. Now notice the ratio is still the same. It's 1/2, and that's -5 over -10. That's 1/2. So I can still solve it by grouping. The problem is that I cannot just add parentheses now without changing the function. Notice that if I just do this, that's not the same function.
No.
because the minus sign would make that a plus 10.
Yeah.
Okay? So when you're grouping and the sign between the terms is negative, you have to be very, very careful. You have to group it.
Okay.
I can always put parentheses around that. That doesn't hurt anything. But here, I have to make sure I don't change it. And the only way to make sure you don't change it is to make that a plus 10.
So you have to change the sign if you put parentheses around that. Okay.
Constant only.
Mm-hmm.
I didn't really change. I guess I did change the sign on the minus. You can kind of think of this as I factored out a -1. But this is the same as that. And yet, I would say 95% of my students forget to change the sign on the constant.
Okay.
Okay? The key when you're doing these is to always check at every step, at every row, to make sure you haven't changed it.
To make sure you still have the same function.
Yeah, we're not trying to change the function. We're just trying to manipulate it so that we can solve it. And the key to that is to never change it. Okay?
Okay.
Now, I can take my x squared out, and I got x plus 2 there, and that's a minus. I can take my 5 out, and I got x plus 2 there. And now I can see that those are the same. If you make that common mistake, you'll notice this turns out to be x minus 2, and this would be x plus 2. You're sitting there looking at it, trying to figure out what the heck happened.
Oh, okay.
Okay? So always make sure these two binomial terms are the same. Otherwise, you can't factor it out. Now I can still factor it out. And now I leave a quadratic that is not irreducible. X squared minus 5 has real solutions. So my solutions, or my linear factors, turn out to be x minus root 5 and x plus root 5.
Okay.
Now I have 3 real solutions.
Okay.
I suppose in the original problem, if they'd have said the real solutions only, then you would have taken it down to that irreducible quadratic. But when they said all of the solutions, then you probably want to take it all the way down to the complex ones also.
Okay.
All right. What else you got?
The next problem is kind of like the inverse of that.
Okay.
So it says in the exercises, find a polynomial function with the real coefficient that has the given zeros.
Okay. What are the zeros?
So, yeah, the zeros are 0, 3, 3 plus I, and 3 minus I.
Okay. Usually they would be tricky and only give you those 3. And they would expect you to know that imaginary zeros always come in pairs, never by themselves. So if 3 plus I is a 0, then we automatically know that 3 minus I is a 0. And it's rare they give you both of them. Usually they just give you one and expect you to find the other. So my factors are what?
Your factors are x, x minus 3, x, is it plus or minus 3 plus I?
It's always minus, and one way that you can always be certain you're right is to put inside parentheses on it. So that's one factor. And the other way, in other words, it's always x minus whatever the zeros are.
Okay.
And now, in fact, when I remove those inside parentheses, I get x minus 3 minus I, and over here I get x minus 3 plus I. So you don't necessarily need the inside parentheses. And in fact, if I simply erase them, I've changed it, but I still have the same two factors. I've just put them in a different order. Okay? So here's our linear factors, and we know all of that's equal to 0. So what's the first step in multiplying these together?
Multiply the x by the x minus 3?
I would do this because when you multiply conjugates, the imaginary always disappears. In other words, this is going to produce an irreducible quadratic that will not have any i's in it.
Okay.
It'll be something like x squared plus 9 or something like that. Something that only produces imaginaries. So let's multiply those two together step by step.
Okay.
I'm going to do it right here, and then we'll simplify it afterwards. So what's the first term?
X times x becomes x squared. X times negative 3 becomes negative 3x. And then doing that twice, you get another negative 3x.
Hold on. Let me give you a little piece of advice when you're multiplying trinomials by trinomials, or for that matter, any polynomial by another one. Stay with a pattern and always use it. And by the best pattern I've used or found is you take the first term, you multiply it by that first term, and then you take that same first term, multiply it by the second, take the same first term, multiply it by the third. Then you repeat with the second term. In other words, you multiply that by that, multiply that by that, multiply that by that. And finally, you take the third term. In other words, you follow a pattern so you make sure you don't forget any.
Okay.
What you were about to do was to kind of jump around. In other words, you were kind of simplifying it before you finished multiplying it. Let's just multiply it step by step. So the third term is x times minus I.
Yeah.
Okay. Keep going.
X times minus I. So next would be multiplying the second term by that first term would be negative 3x.
Okay.
And then negative 3 times negative 3 equals positive 9.
Okay.
And then negative 3 times negative I would be 3i plus 3i.
Correct. Keep going.
Okay, and the last one would be I times x. Will that just come out to ix?
Or xi, yeah. You can put it
xi.
in order. I'm going to put it in the same order as this one because it's going to cancel with this one.
Okay. That would be xi. The next one would be negative 3i. And the next one would be negative I squared.
Okay. Notice what cancels. We got xi there, cancels with that xi. We got a 3i that cancels with that 3i. And the only other I we have is this I squared, and that's actually a real number. Okay? So the end result is x squared minus 6x. What's plus 9 minus I squared?
I squared equals negative 1, so that would be plus 1, so that would be 10?
Plus 10, yes.
Plus 10. Okay.
That's the quadratic you get. And just looking at it, it doesn't necessarily look like that would be imaginary solutions, but it is. In fact, if you test the determinant, b squared minus 4ac, you'll see that it's negative. We'll have 36 minus 40. So this definitely is an irreducible quadratic. Okay?
Okay.
Now multiply the x times the x plus 3. What do you get?
You would get x squared minus 3x.
Now multiply the binomial times the trinomial.
Okay. So you would get x to the 4th times negative 6x, or minus negative 6x squared.
Cubed.
Cubed, sorry.
All right.
Plus 10x squared. And then you get minus 3x cubed. Minus 18, or plus 18x squared. Minus 30x.
And what you always find on these is the n terms don't have any other, they can't be combined. In other words, there's no other x to the fourths, and there's no other x's. So, but what usually can be combined is those middle terms there. So we end up with how many total x cubes?
We get negative 9 total x cubes and plus 28x squared minus 30x.
Yeah, and there's your polynomial.
Okay.
Now, I don't know if, I'm surprised they haven't made this a little tougher for you. And
well, they have another one that.
Well, here's how they would make it tougher.
Okay.
First of all, we know that's equal to 0.
Yeah.
What if I said to you, give me the polynomial that has these 4 zeros, but has a leading coefficient of 2?
Oh, that'd be hard.
Not really. All I would have to do is multiply that whole thing by 2. Notice zeros would still be the same.
Okay.
In other words, because I can always divide both sides by 2 here, and 0 divided by 2 is still 0. So whatever polynomial I come up with is going to have the same zeros, but it would be a different polynomial. It would be 2x to the fourth minus 18x cubed plus 56x squared minus 60x. Now, indeed, that is a different function. That is not the same polynomial, but it's got the same zeros.
Okay.
In other words, if one of them graphs like this, the other one it's twice as big. So it basically becomes a vertical stretch going through the same exact zeros.
Okay.
Like that. So the red one is the 2x to the fourth, and the black one is the function that we originally came up with, just x to the fourth.
Okay.
So just know they're not the same polynomial, but they have the same zeros.
Okay.
In the same way that if I had a quadratic, and a quadratic had zeros at 1 and 4, well, I could draw a different quadratic that went through those same zeros, but it's not the same function. The red is not going to be the same function as the black. The only thing they have in common is that they go through the same zeros. And that one is basically a vertical stretch of the other. Okay? So that's how they can make these problems harder, is by giving you one last thing to do with your polynomial. In other words, they just asked you for a polynomial.
Yeah.
But I've seen lots and lots of questions where they say, give me the polynomial that has a y-intercept of 20. And when you come up with your polynomial, the y-intercept's 10, which means you have to multiply everything by 2.
Okay. Okay, I understand that.
And you may or may not have one that difficult, either tonight or on your test. But given where you go to school, I'd be kind of surprised if they don't give you one that difficult.
Okay. Okay. The next problem is just kind of a refresher on graphing x, y, and z coordinates.
Okay.
So it just says to graph 2, negative 3, 4. And like I remember how to graph it, I'm just not remembering the planes correctly.
Yeah.
And the lines.
I believe that's X. Pretty sure that's Z, and I think this is Y.
Okay.
And
Okay.
I don't do this often to know for certain. You would think the Z would be the one that would come where the X is.
No, I think that's correct though.
Yeah, I think this is correct also. And as all you do is you go in the right plane. In other words, the 2 is the X, so that goes there. The minus 3 is the Y, which is over here. And the plus 4 is the Z. Okay, so if I were to try to find this point, it would be this far on the X, out here on the Y, and up there. In other words, maybe right there would be that point.
Okay.
You can kind of picture it. It's very difficult to draw in 3 dimensions, but that's what this is 3 dimensions. And 3-dimensional problems are always harder. I've always had difficulty with 3 dimensions over 2. I've always felt like I was very good at 2-dimensional math, but the moment I got to 3-dimensional math, it just presents a problem for my brain. Maybe, I'm not sure why, but 3-dimensional solid geometry was always difficult for me.
Okay. Okay, cool.
Now, if you're not certain about this, I could look it up, although I'm not sure I have a book. Do you have a book that gives you?
No, I have the answer key though, and that's what it is.
Okay.
I had to make sure though.
All right. The Y is the horizontal, the X is the axis that kind of comes out of the page at you, and the Z is the vertical.
Mm-hmm. Okay. Okay, the next problem is solving a system by method of elimination.
Okay.
Okay, so it is x minus 2y plus 3z equals 11. And then the next one is 2x minus z equals 3. And the next one is 3y plus z, oh no worries, plus z equals -8.
Okay. So when you have 3 equations and 3 unknowns, which is what we have, the way to solve it by elimination is to try to come up with equations 4 and 5, which only have 2 variables.
Okay.
Okay. And let me look at this for a minute. Let's see. What can we do easily? I don't see where it's going to be really easy to eliminate x and y from both of them, because you have to use 2 different equations to do it. But I can definitely figure out how to eliminate z.
Okay.
And you have to eliminate the same variable for equation 4 and equation 5.
Yeah.
Okay. So what's the easiest, most direct way to eliminate z?
Adding 2 and 3 for the first one.
Yeah. So that creates equation 4, which is what?
It becomes 2x plus 3y equals -5.
Okay. Now, if I go back, I got to find any other two equations to try to eliminate z.
Okay.
Well,
And that would probably...
go ahead.
Could you multiply 2 by 3?
That's exactly what I'm going to do here. That makes
And it becomes 6x minus 3z equals 9.
Equals 9.
Okay.
And now you can add 1 and 2 together to create 5.
Okay.
What do you get?
You get 3x...
Hold on, we're adding 6x to x.
Oh, sorry, 6x. So 7x minus 2y equals 20.
Okay. Now you have the far more common system of two equations and two variables. And we know how to solve this. Let's just make sure you do.
Okay.
What we're going to do is we're going to solve this for x and y and then work our way back through and figure out what z has to be.
Okay.
Okay. So how do I solve this system of equations?
You could multiply them by each other?
No,
Is that,
you need to multiply one by one number and the other by another number. That's
you could multiply the y by the leading or the least common.
Multiply equation 4 by 2.
Yeah.
Both sides. And multiply equation 5 by 3. Both sides.
Okay.
That's certainly something you can do. Multiply only one, you know. And that produces a new equation 4, which is 4x plus 6y equals minus 10. And a new equation 5, which is 21x minus 6y equals 60. And now we can solve, and we finally get one equation and one unknown.
Oh, you can already see that. Okay. So x equals 2.
Right. Now, we got to solve for all three variables. So now we want to go back up into either 4 or 5 to solve for y.
Okay.
We're not going to be able to go back up into the original three equations because, well,
you don't have a...
actually might because they were missing a z, so some of them were. But usually these problems have all three variables in all three equations.
Okay.
Okay. But if my next step is to solve for y, I'm going to go to this equation right here. And I'm not going to go to the one I multiplied. I'm going to go to the simplest one. 2x plus 3y equals minus 5.
Okay.
Okay. Plug in 2 for x. So I now have 4 plus 3y equals minus 5. And now I have 3y equals minus 9. And y equals minus 3.
Yeah, okay.
My second variable solved for. Now, in order to solve for a z, and you could pick the easiest equation, which is this one right here, to solve for z. I'm going to substitute, what was my x, 2?
Yeah.
So I've got 4 minus z equals 3. Take the z over to the other side, bring the 3 over, and equals 1. There's all three solved for.
Okay.
Now, let's talk about something, because these actually, to me, are a lot more difficult than the ones where you have all three variables in every equation. And I've never understood why it's so much more difficult, but I just realized that doing this one, and that's because the variable you have to eliminate is the one that's in all three equations.
Yeah, so this one kind of forces you to eliminate a certain variable.
I think so. We could certainly eliminate x, but then I would have y and z, and then how do I eliminate x again to create equation 5? I don't think I'd be able to. In other words, the only way I can eliminate x is by working with equation 1 and 2. And then I'm done. There's no x in 3. So how do I eliminate it again? The same problem for y. I could eliminate it by working with equation 1 and 3, but then I wouldn't be able to eliminate it for equation number 5. So the only one you can actually do, I believe, unless I'm thinking of this wrong, is to try to eliminate the one that's in all three. Yeah, the one that's in all three equations.
Yeah, okay.
Now, once we solved for x, we could go to this equation and solve for z right away. But then we still have to solve for y.
Yeah.
But of course, then once we solve for z, I could solve for y using that one. So finishing the problem didn't really require us to use elimination. We could have used substitution to finish the problem. But the instruction said use elimination to solve it. So I wanted to use elimination for all 5 equations.
Okay, but I understand where you're coming from getting that third one, though.
Okay, yeah, and like I said, it didn't become clear to me until just today, as the fact that you got to choose the variable to eliminate to be the one that's in all. I think we do.
Okay.
Maybe not, but we certainly.
Well, the next problem I had is one where you have to choose the variable and it doesn't give you a certain choice.
Okay.
So this next one is, because I want to go over this to see if there's a way to identify the best possible route.
Okay.
It is 3x plus 2y plus z equals 17. And then negative x plus y plus z equals 4. And then x minus y minus z equals 3.
3?
Yeah, 3.
Okay. Now, one of the reasons I number these is because you end up with equations all over the page.
Mm-hmm.
And if you don't number them, it's really easy to get mixed up.
Lost.
Yeah, well, or you don't know what you're looking at because there's so many equations. So I number them, and if I'm going to manipulate one of them, I'll just run a line through it and write a new number 3.
Okay.
Which variable do you think would be easiest to eliminate with your first step?
I feel like you would be z.
Okay. Try to think 2 steps ahead. In other words, it would be equally easy to eliminate z or x, correct, with our first step? Or y, for that matter.
Well, the bottom equation and the middle equation, aren't the x, y, and z's just inverses of each other?
They contradict one another.
Mm-hmm.
This has no solution. In other words, I can rewrite 3 to say this. If I multiply both sides by -1, I get this.
Okay.
Right? Well, the left side of 2 is the same as the left side of 3, and the right side's different. That's impossible. You cannot have x plus y equal to 10 while at the same time saying x plus y is equal to 9. Can't happen.
Okay.
Okay? So immediately, by recognizing that, you don't have to do any more work. There's no solution. There's no solution to this, which is a little unfortunate. Let's say we didn't see that. And the way I would approach this problem was, well, I can eliminate z by adding 2 and 3 together. And I can eliminate z by adding 1 and 3 together.
Okay.
So to me, that would be the easiest way to proceed. Well, what do we get? Let's see what we get, because we're going to end up with no solution, but the question is seeing it. Hold on, let's see. Sorry. I'm adding 2 and 3. So I actually get 0 plus 0 plus 0 equals 7. Immediately I see it. So you don't have to necessarily recognize that 2 and 3, the left side of the equations, are the same. We're almost the same. One is just a negative of the other. The fact that the right sides are not anywhere near the same means immediately I see no solution. But if I didn't see that and I decided to add 2 and 3, I get this. And whenever you get one number equals another number, that means impossible, no solution. Always. Whether 2 equations and 2 unknowns, or 3 equations and 3 unknowns. Notice that the one that I gave you as an example, x plus y equal 10 and x plus y equal 9, well, I can add or subtract equations. I'm going to subtract these 2 equations, and I get that, 0 equals 1. That tells me it's impossible.
Okay.
Now, there's one other situation that you have to kind of be aware of, and that is when one equation is just a multiple of the other.
Okay.
Like this. There's 2 equations and 2 unknowns, but not really. They need to be independent equations. In other words, if one of my equations is strictly a multiple of the other one, then it doesn't add any information and I still can't solve it. How would I try to solve it? I would multiply the top by 2. And I would subtract, and now I get 0 equals 0. Well, whenever you get that, it means you have an infinite number of solutions.
Okay.
So there's 3 cases. You can have full solutions. You can have no solutions, which you get when you get one number equal a different one, or you can have an infinite number of solutions, which is what you have more variables than equations. In other words, if I just give you this equation only, that has an infinite number of solutions. I mean, not that x be 1 and y could be 9, x could be 2, y could be 8, but x could be minus 1 and y could be 11. And then obviously we're looking at an infinite number.
Oh, I see how it works. Okay.
So you always have to have the same number of equations as variables, but more than that, they have to all be independent of one another. They can't just be a multiple of another one, and that's what we're looking at here is equation 3. Well, I can't say that equation 3 is a multiple of equation 2, but the left side is. The left side is exactly -1 times the left side of equation 2. Therefore, the right side would need to be negative. In other words, if that was -4, now equation 2 is exactly the same as equation 3.
Okay.
So I really only have 2 equations and 3 variables. And that gives you infinite number of solutions. But the fact that they made it a 3 over here makes it impossible that equation 2 and equation 3 could be correct. Can't have both of them being correct, which means no solution.
Okay. Okay. I get that. Sorry, I was just confused on like how that might work.
Yeah, well, that's also a very I've seen that question on the SAT test, and where they give you 4 multiple choices of a system of equations, and they say which one is impossible or which one has no solution. And so you need to be able to recognize what would give you no solution.
Okay. Okay. Well, the next one's kind of a different track.
Okay.
So it's a word problem.
Yeah, that's fine.
So it says a cylindrical can has a volume of 600 cubic meters.
Okay.
And a radius of 4 centimeters. And it wants us to find the height.
The volume was what?
600 meters?
600 cubic meters?
Yes, centimeters. 600 cubic centimeters,
okay.
Sorry.
Because I thought they were really making it tough.
Yeah.
It really does make it tougher when the units are not the same. Because then you have to do the conversion between how many cubic centimeters are in a cubic meter. And it's not what you might think. It's not 100.
Okay.
Believe it or not, it's like 100,000.
Oh.
100,000 cubic centimeters are in a cubic meter.
Oh, wow.
Why? Because, well,
math is hard.
Well, it's you multiply. It's like how many? If I have 1 yard squared, and there's 3 feet to a yard, what is the square footage of that?
1 times
9 square feet, right? It's 3 feet on each side.
Yeah.
So the base times the height is 9 square feet. Well, if I use yards, it's 1 square yard. So 9 square feet is 1 square yard.
Oh, okay.
Okay. Even though 3 feet constitute a yard. But the moment you go to area, the ratio doubles. And when you go to volume, the ratio is increased by a factor of 3. In other words, there are also 27 cubic feet in 1 cubic yard.
Okay.
That's why when you gave me centimeters and meters, I said, oh boy, we're going to have to make sure we find out that relationship.
Huh.
But they didn't make it that hard. So, all right. And they want to know the height, right?
Yes.
Okay. What do we need?
We need the equation for the volume of a cylinder?
That is a prism. What's the equation of all prisms for the volume?
Oh, man. I'm unsure.
Well, what have I said? The first part's the area of the base. What would the second part be?
The area of the base times the height?
Yeah. All prisms, no matter what kind of base you're dealing with. I could have a triangular base. And as long as it had an equal and opposite triangle on the other end, then it's the area of that triangle times the height. That's what the volume of all prisms are. Even if you take a rectangular brick, we know that the height on a or the volume of a rectangular brick is all 3 dimensions times one another. But what it really is if that's x and that's y and that's z, Well, it's the area of the base. This is a prism. That back object at the end of the rectangular brick is identical to this face.
Okay.
And in fact, if you were to cut this thing with a knife, no matter where you cut it, as long as you cut it perpendicularly, you will have a face that has the same dimensions as this.
Okay.
This is a prism just like your cylinder is. I'm going to take the area of the base, x times y, and multiply it by the thickness of the prism, which is z.
Okay.
And so you end up with x times y times z. But that's the area of the prism.
Okay.
Okay. Now, so what's the area of the base? That's a circle. What's the area of a circle?
Isn't it radius times pi squared? Or pi times radius squared?
Pi r squared.
Pi r squared.
Times the thickness of the prism, h.
Okay. And that's the volume of the cylinder.
That's the volume. And now it's a piece of cake. In other words,
Yeah.
now you substitute 600 for there. You substitute the radius of 4 squared. And now the only thing to solve for is h. H is going to be 600 divided by 16 pi. And you could simplify that a little bit. You could certainly cut everything in half. So that'd be 300 over 8, which would be 150 over 4. And I think that's as far now. I can still cut everything in half. That's 75 over 2 pi. Pi stays in the denominator.
Okay.
So that's h, simplified.
Okay.
Which kind of introduces an interesting question. How come we can have an irrational denominator here, and yet if I gave you this, that would be incorrect mathematically. I'd have to rationalize it to square root of 2 over 2. Reason is that I can rationalize that. I can't rationalize pi. It's impossible.
Is that because pi is a number, or?
Well, it's an irrational number, and it's also called a transcendental number. And the fact that it's like e. You also cannot rationalize e. Both of them are irrational, meaning I can't write them as a decimal. I can't write them as a fraction.
Okay.
Accurate representation of pi is pi.
Okay.
I better be careful how I say that because that's my dog's name. He'll be
That's funny.
up here if she hears me say that real loud. But that's the reason we can get away with having it in the denominator. We still have an irrational denominator, but there's nothing we can do about it. I can't multiply top and bottom by anything that changes this irrational denominator.
Okay. I understand that.
Yeah. Just a little interesting piece of math. And that's why you end up frequently seeing answers that have pi in the denominator. Or e.
Or e.
You got like 4 minutes. Is there any
that's what I was just actually looking
questions
for.
you have or a specific problem? We can probably do it in 4 minutes. That one was real quick.
I'm just sorry. I'm just scanning through to see if there's any real quick ones. Can we go over the change of base formula real quick?
Sure. You can't get that directly out of your calculator, or unless you have an Inspire. You have an Inspire?
No. I'm sorry.
You have a TI-84 that only has 2 keys on it, common log and natural log.
Okay.
So there's no way to get the log base 2 of 7 unless you use the change of base formula. And the way I remember it is it's always the log of the upper number, the 7, divided by the log of the lower number, or the base. And it doesn't matter what log you use. surprisingly, that ratio is the same as this ratio. And in fact, it's the same as this ratio, log base 17 of 7 divided by log base 17 of 2.
Okay.
All these log ratios are the same despite their different bases. So usually you use common log. And then now that you can get out of your calculator because you have a key on there that's common log. But I actually end up using that almost exclusively. And I'll tell you why. When you get to calculus, natural log is the log of choice.
Okay.
Natural log actually is one of the definitions of a very key part of calculus. And you end up working with natural log about 95% of the time. Not any other log, not even common log, but certainly not logs of other bases very often. So if I'm solving an exponential problem, I'm always taking the natural log of both sides, even if I have something like this. 2 to the x equals 7. If I want to solve that, I'm always taking natural log.
Okay.
And the reason is that now I can bring the x down in front. So x is equal to the log of 7 divided by the log of 2.
Okay.
And it might look like it was 2 steps, but the reality is some people would be inclined to take the log base 2 of both sides.
Okay.
Because that produces the x immediately. But now you've got this expression over here, and I can't do anything with that, not certainly with the TI-84 calculator. I got to apply the change of base formula to it. So there's still that third step. So I haven't really saved myself any steps by taking the log of 2 of the right side. Since you don't save yourself any steps, I don't ever do it. I just always take common log or natural log.
Okay.
Just immediately I'm going to take the natural log of both sides. And it's occasionally quite useful if there's an e over there. In other words, if I have that, now if I take the natural log of both sides, I immediately get x. X is equal to the natural log of 7. So one step using natural logs.
Okay. Okay. Cool.
All right, Nick. Let's see. We have another session, don't we, this week?
I don't think so because this is my last week.
Oh, no. Yeah, you're right. So your test is probably Monday?
Yes.
And I don't have any other set. Okay. Well, cool. Your mom told me that you're doing better.
Yeah, I have a B now. If I just get a B on the final, I can keep it.
Well, do it. That'd be great.
I know.
That'd be great.
Mm-hmm.
All right, Nick.
Thank you so much for the help.
You're absolutely welcome. It's been a pleasure working with you. And when you get to Trig next semester,
I'll be back.
Come ask for my help. I love tutoring Trig almost more than any other subject.
Okay.
But I will tell you that it is a lot of memorization. More so than any other math you've had.
Okay.
All right?
All right. Happy holidays, Mr. Cohen.
You too, Nick. Talk to you later. Bye-bye.
Bye-bye.